We are now shifting gears to the other fundamental topic in the study of calculus besides differentiation, and that is integration. We are going to start with the question of the area under the curve. And what we're going to do here is consider the function y equals x squared, or f of x equals x squared, and we are going to evaluate the area under the curve from the point 0 to 1. Okay, so we're looking for that area contained in there. Now, we don't know how to do it, okay? Like, we're stuck before we get started. So it's a curve, right? It's not a nice rectangle, so what can we do? What we can do is approximate. And one idea for an approximation is to subdivide this curve into rectangles. And we approximate it by taking the area of the rectangles. So for instance, if we split this into 4 rectangles, first of all, what might that look like? Okay, so you could divide it in half and then half again. And then in each case, you go up and you're getting you want to get a rectangle. You don't have one yet. What you have now is a partition. So how do you get a rectangle? You've got to make a choice about what the height of the rectangle is going to be. So what we'll start with to keep it simple is we'll look at the right side. And what that means is if we're looking at this first point, we're going to make a rectangle by connecting the right side of it to the y-axis. So same thing here, go up to the next one, we get the right side, go up again, we get the right side, go up again, we get the right side. And so what we have now are 4 rectangles that we can use to estimate the area under the curve. Okay? Because we're using the right side of the endpoints, this is actually called a right-hand Riemann sum. And let's go ahead and compute it. Now to compute it, we need to know the base, the length of the rectangles. That's often called delta x, and delta x here is what? Well, if we're splitting it into fourth, each one is a fourth, okay? But I'm going to go ahead and give you a formula that will be useful later. FYI, it's b minus a over n, so 1 minus 0 over 4 gives us 1/4. Okay, great. What else do I need? What I need to know the, so we've got these points on the curve. This one got a little missed because it's close. And to get those individual points, I need to know exactly my partition. I need to know what am I looking at here. And what I'm looking at, I'm starting with the point 1/4, then I get 2/4, right in the middle that's a half, and then 3/4. And we got one more because we got this final rectangle. Make it in pink there. It is a height of 1, which is 4/4. You might wonder why is he writing it in fourths? I'm just trying to make it clear how we're getting it. Okay, so all that's left now is to compute the actual area. And so the way we do this is a right-hand Riemann sum, and we just sum up all the base times the heights. Okay, the bases are all 1/4. Now these are the different heights evaluated at this function. Okay, so right, the height is not 1/4. The height is, that's the point on the curve. It's 1/4 squared and 1/2 squared and so on. Okay, so to get the sum, all these rectangles, 1/4 times 1/4 squared plus. And then you just keep going, you keep adding them. They're always going to be a fourth for the base, and the height is going to be the function squared. And then we just keep going, plus 1/4 times 3/4 squared, plus 1/4 times 1 squared. Okay, and we can add this up. Let's go ahead and do it. A little bit of a pain, okay. So the advantage of keeping the force is you get the same denominator. also. And you could or could not factor out the fourth. I think it's good to potentially leave it. So when you square the fourth, you get 16, and then 16 times 4 is 64. So what are we going to get here? We're going to get 1/64 plus, again, just think of it as 2/4. I wrote a half, but 2/4, right? You square it, you get 4/64. Denominator is always going to be 64. Plus, that's more clear here. You can see you get 9/64. And again, with the 4/4, it should be clear you get 4 squared is 16/64. So how many 64s is that? Well, it's 25 plus 4 is 29, 30 out of 64, right? Is that right? And then we can divide by 2 to get 15 out of 32. Okay. Now, 15 out of 32 is overshooting, right? Because we chose the right-hand sides. So, can we do better than that? Of course, we can use the left-hand sides. I mean, it's not better, okay? Better, the left-hand side will provide a nice balance. Let me show you what I mean. So what we're going to do, we're just going to replicate this again. We have f of x equals x squared, and we have our function evaluated between 0 and 1. And we're going to subdivide it again, but this time we're going to use the left-hand side. So let's see how that works. Okay, so we've got our halfway point, quarter points. Now, if you're using the left-hand side, okay, this is kind of weird. So if we look at this first one, here's the left-hand side of the rectangle. It's flat, it doesn't go anywhere, okay? If we look at the second one, the left-hand side is here. Third one, see what you do, you draw up, and then, I mean to draw this one up, and then you go to the left. Yeah. And so there we have what would be called a left-hand Riemann sum. Now, our partition is similar, but a little bit different. Delta x is the same. So what's the partition? Well, the first one, like, it's the heights. Okay, so it's 0, and then this one I use a fourth, 2/4, and then 3/4. Right, these are the different heights of the different rectangles. And again, delta x, same, is going to be 1/4. Okay, delta x equals 1/4. So now we get a left-hand Riemann sum, and let's go ahead and compute this one now and see what we get. So it's always going to be 1/4, and then it's times 0 squared, plus 1/4 times, I realize this should not be 2/3, this should be 2/4. Okay, 1/4 times 1/4 squared, the second one, plus 1/4 times 2/4 squared. Finally, we get 1/4 times 3/4 squared. And what we're going to get is a left-hand Riemann sum of, first one's 0, so we've got 1/16 plus 64ths, right? The 1/16 is true, but times a fourth gives you 1/64. And it's kind of interesting because you're getting sort of the other ones, but you're getting less of them. Plus 4/64ths, plus 9/64ths. And so if we add all of the, putting threes, if we add all of this up, we get a left-hand Riemann sum of 14/64ths divided by 2, we get 7/32. Okay, so what we know from these estimations is that the area under the curve of f of x equals x squared is going to be between 1530 seconds, which is an overshoot, so it's an upper bound, and a lower bound of 730 seconds. Okay, so how can we do better? Okay, we've got a lot of different options to do better. Now, one of them you could certainly imagine is by adding more rectangles. Okay, we chose 4. I chose 4 because I can draw it. Sorry, my drawings aren't the best, but you could certainly do more. right? You can kind of imagine it. You know, maybe we'll just put up an alternative here. You can see what I mean. So if we do f of x equals x squared, do it again. And now, okay, we do like, instead of just 4, okay, we could do like 8. Okay, so if we do 8 on this one, okay, split it in half, fourths, you do the halves again. And now you can imagine wherever you're making the rectangles, you're going to get a lot more. And so let me just keep going up and over. Pretty hard to draw here because they're a little bit thick. Okay, and when you get something like that, okay, so you end up with a lot more rectangles. You can see you're going to get a better estimation. So the more rectangles, the better estimations. Another thing that you could do, why are we using the right and left endpoints? You'll find out. But you could certainly use the midpoint because if you take the midpoint of these, it's going to be nicer. We can look at that one maybe just in terms of the fourths. Okay, so if we do, let's do another one where we've got the same f of x equals x squared. And what we're going to do here is look at the midpoints. Okay, and again, we'll just do this one with 4. So if I do the midpoints, okay, first got to get my halfway point, second, third. Well, now you come in the middle to get to your rectangles. And clearly this is a better estimation. So the idea here, you find the point, go in the middle, and you use that to draw your rectangle. And the reason why this is better is because you're getting middle. You're getting like you're overshooting and you're undershooting. So it's going to balance out and give you a better estimation. Okay. So you can get great estimations. These are okay. You can do better, right? You could use a calculator. You could do like 50 triangles, 100 triangles, 1,000 triangles. Sorry, rectangles. And what you'll see is this is going to get closer and closer to 1/3. Okay? So the next question is, can we figure this out exactly? Can we do some kind of a process, like with limits, where we use not a finite number of rectangles, but an infinite number of rectangles? That's what we're going to try. Okay? So the first thing we need to do is formalize this process. Now we kind of did it, we started it with this delta x equals b minus a over n. So I'm going to put that up here because it's important. Delta x equals b minus a over n. And what else do we need? So when we're computing these partitions, what we need to do is set it up so that you're not just like putting in the number, but you're figuring out how you do it. Now the key here is look at the b minus a over n. In this particular case, this is 1 over n, and it's 1 over 4, right? And the 1 over 4 is within the partition, and then you're just taking like a bunch of these, right? 1, 2, 3, 4. So the partition looks something like this, okay? Now whether we use left or right for an infinite number isn't going to matter, okay? We'll put them all up. So you have 0, and then what do you have? You would have, it's 1 over n, okay? Right, if it's 1/4, but if it was an 1/8, here it would be 1 over 8. And then you have 2 over n, right? And then you have 3 over n. And what do you end up with at the end here? You end up with 1, which is n over n. Okay? So that's what the partition looks like. Now, let's try one of these. Let's go with the right-hand Riemann sum. And so what we're going to do here, we're going to set this up Okay, now we can factor out the 1 over n, right? Because it's here in each term, 1/4, 1/4, 1/4, 1/4. For approximation, it's easier to leave it in sometimes, but we're going to factor it out. So we got a 1 over n. Now, what are we multiplying this by? We're multiplying it by each of these terms, but these terms are going to be like the inside of the function, which in this case is f of x equals x squared. So we've got 1 over n squared plus 2 over n squared plus dot 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 n over n squared. Okay? Now, recall we're not specifying how many, okay? Yet, so we can simplify this a little bit and we get the following. So we can note that we can factor out the 1 over n squared. We're left with the outside of a 1 over n cubed. And then on the inside, it's just 1 squared plus 2 squared plus dot 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 all the way up to n squared. Okay. What do we do now? What you do, you take the limit as n approaches infinity. Okay? And again, why are we doing this? Because we're trying to generalize this process so that it works not for a finite number of rectangles, 8, 16, 50, 100, we did 4, but for an infinite amount, right? And if you do an infinite amount of rectangles, the idea is they're going to be infinitesimally small. The height is going to be perfectly the curve, and your answer, we think, hopefully, will be exact. So we're going to take the limit. Now this actually will give us the area. The limit as n approaches infinity of what? Of this thing. 1 over n cubed times what? Okay. So when you're doing summations, this is a summation, and we'll talk more about summations, you sometimes need a formula. And this is a formula you would look up in a text, okay? I can tell you, I do not have it memorized. I'm not sure how many people do. So the formula, if you're summing a bunch of squares, is the following. It is, in fact, n times n plus 1 times n plus 2 all over 6. Okay? That is the formula for the sum of the squares. Now this becomes a straight limit problem, and we can do a straight limit problem. So what's the area? Okay, knowing your limit tricks, you only have to look at the leading powers. So let's look at the numerator. What's the leading power here? Let me get this right. No, this is 2n plus 1. Okay, it's not n plus 2. So this last term is a 2n plus 1. Okay, sorry about that, 2n plus 1. Okay, so the leading term in the numerators is n times, it's going to be a 2n cubed. And then we have smaller terms. And then your leading term in the denominator is going to be a 6n cubed. Now, if you remember your limits, okay, you should not care what the other terms are because they're descending. They're smaller powers of n. As n goes to infinity, if you divide by n cubed, all those other terms will go to 0. And you're left with the leading coefficients, which is 2 over 6, which gives us an answer of 1/3. Okay? This is the correct answer. This gives you the area under the curve. So what did we do? Seems like trickery. We started by approximating the area under the curve using rectangles and, just approximating. But then we make a jump. And to do the jump, we consider, can we do an infinite number of rectangles? We set it up delta x equals b minus a over n. We partition it, okay, going from 1 using the right-hand sum all the way to n. And then we compute the limit as n goes to infinity. What that is, that's the number of rectangles. So if you have an infinite number of rectangles, okay, it appears to give us the right answer, 1/3. It is the right answer. It becomes a limit problem. And there's a lot more to this that we will discuss, okay, that will be revealing. But it starts out as a limiting process, and it does give you the exact area. We are not going to prove that. Proving that a Riemann sum, the limit as n approaches goes to infinity, is in fact the area under the curve, is beyond the scope of this class. But if you do the computations, you will see that it in fact works.